seconds, and we're live.
Okay.
We're on air.
Excellent. So thank you, Alex, for having me, and thank you all for your time today. I really enjoy getting to introduce H2O. So couple of things. H2O is an open source Apache version 2 licensed machine learning engine. And so I'll go through a little bit more about that and kind of what all that means. But it's really designed for doing machine learning on data that won't fit in a single node on a computer. So it's designed for distributed processing of really large data in memory. So real quick, Alex already did a great introduction. I work at H2O as a data scientist and hacker. My primary thing is I help customers figure out how to use H2O in their business. So there is a commercial venture behind the open source product or open source software. So I'm gonna because my employer is what gives me the time to go do this. I usually share a little bit about that. Then we'll get right into the product. So the H2O was started in 2012 in Mountain View, California. So it's an open source product that was started out of a company. So it wasn't, unlike some other open source products that come out of a community, it was started because there was a company that started the product and then made the software open source. The team that works at H2O is about 40 people. They wake up every day and they think about how to do better machine learning applications at scale. And unlike other companies that do machine learning, a lot of the focus has been hiring in the core engineering group, which is out of 40 people, about 30 of the team, focusing on people that are systems engineers, as opposed to, we hire statisticians and mathematicians, but the real focus has been hiring people that know how to do kind of data at scale. These are kind of the executive team. Sri Satish Ambadi's the co-founder and CEO. He was previously at DataStax. Cliff Click is the company's CTO. He was co-inventor of the Java Hotspot virtual machine. Cliff writes about 30,000 lines of production Java code a year, all of which is focused on high performance code. And then Tom Kralevec is our vice president of engineering. This is a picture of the team. If you go out to the website, you can actually get a little bio on everybody. We rely heavily on our scientific advisory council. So Trevor Hasty and Rob Tibshirani and Stephen Boyd help us, every day. They're really great to have because as we're trying to figure out how to take these machine learning algorithms that were designed to work maybe single-threaded or just on a single machine and make them work in a distributed environment, we can call them up and ask them, like, does the math still hold? Is it still true? I'll cut through, some of this is marketing, so I'm gonna cut through a lot of this real quick. So one of the things is that, and you'll see this in the design of the software, which I think is the reason to have it up here. One of them is that speed matters, right? So the customers that are using and the users of H2O are focused on speed and accuracy. So everything that happens inside of H2O, so one, data is completely loaded off the disk into memory for doing the machine learning portion. And so all those iterative machine learning algorithms happen in memory and happen fast. So we believe that you can get more insights when you don't sample your data. So a lot of times people spend a lot of time and energy figuring out how to make data fit into scikit-learn or R, for example, whereas H2O is designed to be distributed across a cluster of machines if necessary. And there's things to make it easy to use, like an interactive user interface that I'll be showing shortly, and also making it easy for developers to use. So there's R APIs, Python APIs, there's Java APIs, REST APIs. So there's all kinds of ways to get at H2O. And then, the focus has been on kind of industrial strength algorithms and making those available. And then making, once you learn the function, right? When, machine learning, you look at data and try to learn a function, make that available so people can do scoring on new data very fast. And there's a market term for it called the NanoFast scoring engine, but I'll actually show what that is here in just a few moments. This is a little bit of a architecture slide, but it gives a picture of kind of what H2O is. So think of H2O as the yellow box, and everything that's not in the yellow box is the ecosystem that H2O lives in. So first, H2O doesn't really care where it runs. It will run standalone on your laptop. It will run in Hadoop clusters to get access to the Hadoop, those resources in Hadoop and HDFS. It will run inside of Spark. And it will, if you want to do distribution, you don't want to use Hadoop or Spark, it will cluster on its own. So you can actually build a distributed cluster of standalone H2O nodes. The other piece is that the algorithms need to go to where the data is, and H2O tries to be very agnostic as to where data comes from. So it has native support for just your file system for HDFS and S3, for SQL and NoSQL engines, either doing a pre-extraction to one of the file system HDFS or S3, or using a Spark connector to get data from those. So it doesn't really care where data comes from. And I've already mentioned it before, but up along the top, we want to go wherever data scientists and developers are. So there's a R API that I'll be showing today, a Python API that's really brand new, but matches in features the R API. If it's running in Spark, you can get at it through Scala. It's also got a Java API, which is the same API mostly that you get at it from Spark. It has a RESTful API, so you can send it REST commands and get JSON back. And then there's various ways to embed it in business intelligence tools like Excel and Tableau. Inside of the core of the H2O software, when data gets loaded, it gets loaded into memory, and then it's spread across the nodes by row. We've got several in-memory columnar compression techniques that typically get 2 to 5 times the compression of disk and memory, so make very efficient use of memory. And on top of that is built a parallel distributed processing framework. It's actually an in-memory MapReduce framework. So not the MapReduce that's in Hadoop, but an in-memory MapReduce framework. And on top of those, that's where all of the machine learning algorithms are built. Again, once you learn these new functions, you can get out a plain old Java object that is what we call the NanoFast scoring engine that you can then go take and put anywhere that you want to do scoring. And then there is a user interface that comes with it for playing with. In terms of machine learning algorithms, there's a set of supervised learning algorithms and unsupervised learning algorithms. On the supervised learning algorithms inside of H2O, we support, it supports currently in version 3 generalized linear models. Lasso, ridge regression, elastic, and plus different distributions, so binomial for classification, and Gaussian, gamma, Poisson, and Tweedy distributions for regression. a naive Bayes classifier available. On the ensemble set, it supports a random forest, and it'll run random forest distributed across nodes. So you can put really, really big data in and learn a random forest. And those support both classification and regression. There's also gradient boosting machines. So this is an ensemble of decision trees, right? So, and H2O had the first parallel implementation of and distributed and parallel implementation of gradient boosting machines in the world. Also, there's a deep neural network. It's a as it says here, a multi-layer feed-forward neural network with layers of nonlinear transformations. It supports regression and classification and different loss functions, multinomial, binomial, Gaussian, gamma, Poisson, and Tweedy distributions, and is one of the few open source pure Java implementations of neural networks. So that's the other thing to kind of mention about H2O. It's all 100% pure Java. So the only requirement to run it is a Java virtual machine. The unsupervised algorithms that are available are k-means for clustering, principal component analysis for dimensionality reduction, and then finally the deep neural networks can be configured as autoencoders. So you can use them for things like nonlinear dimensionality reduction, or since you're trying to learn the identity function, they can be used for finding classes that are nonlinear outliers. This is the typical way people use H2O. So one, they ingest data into this modeling engine, do feature engineering and data munging, and then machine learning, and they produce out a Java object that is the learned machine learning algorithm, and then new data is typically streamed through that nano-fast scoring engine to be able to score new examples that come in. So I'm gonna switch screens here, and I'm gonna show you kind of Flow and H2O and all the things I've been talking about. So first I'm gonna show through the Flow user interface, and then I'm gonna show H2O through R. So this is the Flow user interface. No matter where you run H2O, this user interface is available to you. So if you started inside of R, you can there's directions on how to access it. So typically the first thing needs to happen with H2O is to read in a little bit of data. So the data I'm going to read in is commercial U.S. airline data flights from some of 1987 through 2013. Try to read it in. So there's a couple steps, and kind of because of how H2O does its parsing, it's there's just a couple steps, and it makes a lot more sense when you have lots and lots of partition files to go through those steps. So this is the parser. It's read a portion of the data. It's tried to guess what the data formats are. So natively inside of H2O, it supports delimited formats, Excel formats, SVN-Lite, and ARFF. There's new formats coming online in future versions, and if you're using it inside of Spark, you kind of have all of their formats supported. The data types that are supported by H2O are numeric data types. So it is the data when it gets loaded into H2O gets loaded into a data type that we call it's called an H2O frame. It's much like a Pandas data frame or an R data frame or a data frame out of Spark, where you have you can mix different data types inside of the same data structure. Each column or feature has support for data types. So we support numeric data types, enumeration or factor data types, time data types, unique identifiers. If you have, one of the things that we do specifically is we call out strings different than enumeration data types. So if you have a high number of factors that are represented as strings, sometimes it's better to represent them as strings in terms of the learning. So the other piece, so I'm running this. There's help for flow if you want to get started with it. What I want to do is I want to pull out a window. This window, so I'm running H2O in Amazon Web Services today on a 8-node, 8 CPU per node cluster to kind of demonstrate the parallel capabilities. So when these bars are blue, it means the CPUs are sitting idle, and when they're green, it means that they're busy doing stuff. So we'll parse in this data. This data sits at about 16 gigabytes on disk. So it's actually kind of small data for what a lot of people use it. So it's 150 million records or so. But you can see here, even parsing and loading into memory is done in parallel, so that file's partitioned and loaded in parallel to speed even the loading from disk to memory. So this is, like I said, being sprayed across those 8 nodes. It's being basically row sliced, so row partitioned across those nodes. And then it's being compressed, which is kind of this, some of these last steps you see happening here. So that was 150 million records, 16 gigabytes, 45 seconds or so. So we can look at summary statistics for this. So I ran the equivalent of like R summary command. Like I said, it's about 150 million records. It's got 31 columns in it. In terms of the H2O frame, we can look at univariate statistics. So this is a histogram that was created across the 150 million records. This represents the number of flights per year in that histogram. Over that period, we only have partial 1987 data and partial 2013 data. You can look at, for instance, which months people travel more. So this is integer encoded months inside of the U.S. commercial aviation for that time period. Again, this is a histogram across 150 million records. It's kind of a click of the button. So the next thing to do typically is, if you're doing machine learning, is to do some splitting of the data. So you can, in Flow, there's a couple ways to split the data, or one way to split the data. You can do training, validation, test splits this way. So this will create random splits. I'll show you some other mechanisms. If you're driving it from R or Python or Scala, you can, there's all kinds of other, you can split however you want through those. They provide more functionality in the R interface. So we'll create these. So this is randomly splitting that data up. So it's actually creating 150 million random variables, random uniform variables, and then running a split algorithm on it so that they are all shuffled and split, and then sprayed back across those nodes. So now we'll actually go and build a model. So everything I'm showing you kind of in the Flow user interface, the reason I show it here is because it's all also available in the, will be available through the R API. So we'll pick our training frame here, and then we'll pick our validation frame. Also, H2O supports not just training and validation, but also in-fold cross-validation, and you can do both if you want. So you can take your training frame, do in-fold cross-validation, and then use the validation frame for something else. So all kinds of different mechanisms for being able to do cross-validation. I'll pick a response. We'll do a classification problem for this demo. So we'll predict if the if the flight was delayed in its arrival. we've pre-processed this data, so there's lots of predictors in it. So I'm going to leave in which year you were flying, which month the flight was in, which day of the week the flying was, when the computer thought you would depart, when the computer thought you should arrive, who the carrier is. So you can see the carrier is an enum that's got 30 different entries. So this is 30 different airlines. This will be one hot encoded because we're inside a generalized linear model to 29 columns automatically. H2O. The other numeric columns that you see here, integer, will be, they'll actually automatically be standardized, so there'll be 0 mean and 1 standard deviation. And then we'll leave in where the flight originated from, what its destination was. And again, these will be one hot encoded. And then we'll make sure we put in the predictor column, which is, are you going to be arrival delayed? So this, this few number of predictors will expand out through one hot encoding to about I think it's 768 features in the data set. So when you think about this, what we're doing is we're actually learning a model on 760 features and about 75 million records. Like I said, we have support for all kinds of other things that we won't go into detail here, but I will set this to be a lasso regression, so I'm looking for a sparse model, and then I'll leave all the defaults the same. All the H2O algorithms have various different configurations that are documented and are available in the user interface to look at too. So stopping requirements, all those things. So we'll kind of hit to the piece here. So here you see, this is, like I said, a generalized linear model. As a developer or data scientist, you don't have to worry about the fact that it's distributed, except for knowing that you have enough CPUs to do your job in the time frame that you want. So if you wanted this to run twice as fast, you would just give twice as many CPUs. In this case, I've got plenty of memory. The memory requirements are usually between 2 to 5x what the data size is in memory. So this 16 gigabyte file on disk compressed down to about 5 gigabytes in memory. So typically we'd expect to assign somewhere between 20 and 50 gigabytes to the overall H2O cluster, just depending on how many models you're going to build and the model complexity. So you can imagine if these nodes all have, I think these are 256 gigabyte nodes, I have lots of room to load up data and do scoring on them. So that's done. It took 40 seconds to build a model and score it on the validation data set. When H2O does this, it does all of its calculations. It does calculations for all of the metrics as part of the process, so it's not an extra step to calculate the metrics. They're all, and if you're in R, I'll show you, it all gets returned to you so you can take a look at it. So you get things like, because this is classification, you get the area under the curve, and you get the full ROC curve. You both get that for the training and the validation data. If you're doing cross-validation, in-fold cross-validation, you get it for each of the cross-validation sets that you can look at. There's various cut points. You can look for the max accuracy cut point. The confusion matrix for all of the cut points are all calculated and returned and available to the client. Since this is supervised learning in GLM, all of the beta coefficients, so the coefficients in front of the linear model, are returned and available. If anybody's traveled to the US, you'll know that if you're leaving Atlanta, you're likely to be delayed getting to where you're going, or Chicago, or Newark Airport in New York. If you're going there, you're likely to be late. So it tells you, even without having a great predictive model, right, you get insights into your data very quickly on large data. It gives the scoring history, how fast the objective converged. This one only did 5 iterations before it stopped. All of the validation metrics are available, so all of various validation metrics are calculated. So in case of classification. You get all of them, but maybe the most important ones are looking at things like log loss or area underneath the curve or the deviance that's available. And then finally, that fast scoring engine I talked about. So this is the Java object. So this is a representation of the model that was just learned. This has a this has a method in it that's called score zero that will take in new data and return new predictions. So not only will you get, since this was a classification problem, not only will you get a 1 or 0 based on the F1 cut point, was this delayed or not, would you predict that this flight would be delayed, but you also get the probabilities of class membership. So probability of being delayed or not are both also available. So you get 3 columns, so you can decide your own cut points. These become really important when you're doing like multinomial classification, because then you can use it for ranking of the predictions and showing those to users. But this is the method. All the beta coefficients are hard coded in here, and the reason is that it makes this Java object. It will run in the L1 or L2 cache lines of a CPU and score new predictions in approximately 90 nanoseconds for generalized linear models. So that's the NanoFast scoring engine, and at the top of it are directions, so you can automate the whole process of building this model, getting it downloaded, compiled, and then using reflection or whatever method, loading it into wherever you want to do scoring. So you can do the compilation and reload it into a Spark Stream. You can load it up into a Storm Vault. You can. We have some users that are actually compiling it and deploying it out to the edge of their network, so that they like at a point of service. So there's all kinds of places you can go take up Pojo. I've also built some other models before we got here. So GVM models are GLM models, unless they're very high dimensionality, which happens a lot with things that are like text-based and very sparse. They often don't benefit from having lots of rows, but gradient boosting machines will benefit from lots of rows. And so I had previously taken that exact same data and built a default H2O GVM model. And you can see here you get kind of the training and validation MSE available. And in this case, this model probably hasn't converged and could stand to have more trees built before it would reach its maximum predictive strength. But you can see here, like the ROC curve on the validation metrics for the previous data was 0.60. This one's 0.63. So it's a little bit better, and it's learned some nonlinear interactions. So it's learned things about, it turns out it's learned things about which month of the year you're traveling in versus the day of the week matter for being able to predict this arrival delay. You do get out variable importances, and just kind of to underscore, the Pojo comes out with all kinds of Java objects available. So I've probably showed enough of the Flow user interface since this is an R session, but it provides some background. So this GVM model is available too. So everything produces these Pojos. These are the trees. Trees score in about 30 nanoseconds times the number of trees times the average depth of the tree for new predictions. So they run fast too. So in R, which is what I want to go to, and I'm going to run this on my laptop. So if you want to, one of the things about H2O is that we do, the company does all the builds for you. So everything is in open source. It's in GitHub. There's no private repos. So you can go out and take a look at it. Even the upcoming training session is starting to be put, H2O World, which will be in November, and Mountain View is out in public repo. Our meetups and all of this are available in repos. So there's all kinds of things out here that are available as part of the H2O repos that are all public. If you want to get started inside of R, you can go to h2o.ai and hit the download button. If you go to, I'm actually going to use Bleeding Edge today, but if you want the latest stable release, and there's new releases about every 6 to 8 weeks. If you want to download it, you can download it and run it locally, and this will start up H2O, and the Flow UI will be available. But to install it in R, there's a set of directions for installing in R. So you just copy and paste this chunk into your R command, whatever you use, and it will install H2O. Now H2O is in CRAN, and you can get it out of CRAN, but CRAN always runs a little bit behind our own releases, so it's usually better to go get the latest release from here. So I've already done the install, so I'm going to just start by loading up the MSF, the H2O library I already started. The first thing to do is, if you're using it in R, is to actually start H2O. This command right here will either start H2O locally, or you can specify an IP address and port and connect to an existing H2O instance. So in this case, I'm actually starting H2O. So I've started H2O out of process of R, pure Java. It's running on my machine, but it's out of the R process. So it has access to as much memory as I've allocated the Java virtual machine, which in this case is only 4 gigabytes. My little laptop only has 4 cores, and I gave it access to 2, and all those are available in the init commands. Again, just like through Flow, to load data, you just run. In this case, I've got 2 data files I want to load. I want to load up a training data file and a validation data file. Much like I was changing things that were integer encoded to enums before, I'm programmatically doing that through this set of steps. So it turns out columns 11, 12, and 13 are integer encoded in these data sets, and I want to set it up so that it reads them in as enumeration types. And so I'm loading up the training data set and the validation data set. These aren't terribly big. What we've done inside of both R, especially in R, and are doing more inside of Python is that we're making, so these are H2O data frames. So you can look at them. I'll just run it here real quick. So this is, this returned the first 10 rows of that data that I've loaded, but it's an H2O frame. But we make things like the R summary command work on that data frame. So this is summary statistics, just like you would do inside of R normally, except it's running, that actually goes out to the remote machine and runs. So this actually issues a REST command to the H2O server that's running out of process and says calculate summary statistics. The same thing here. So I'm just going to set up a simple model for building. So I'm going to build a random force model. So this is getting built on my machine, and while that won't take very long to build, I want to kind of go back to my slides real quick and show you I want to explain a little bit more about what's going on in the interaction between H2O and R. So this is what's going on. So I read the import file, and if I were running H2O, let's say we're running in a Hadoop cluster with multiple nodes, what that actually is doing is it's issuing a REST command to the running H2O instances that are over in the Hadoop cluster to one node of it. They're actually peer-to-peer nodes, but as a client, you connect to one node. That central node sends commands to all the other nodes to say, ingest this data into H2O. That data is read in parallel off the disk into memory. And then a pointer to that data that's been loaded is returned to the R client. So there's no data other than just enough to pass pointers back and forth that are returned to the client. So I've built that random force model. I get a small representation of it back on the client. And as you can see here, you get kind of all the things you saw in the H2O frame. You get, this one was multinomial, so while I defaulted to 50 trees, there were 7 classes, so I built 350 trees. It tells you a little bit about the depth, how many leaves there were per tree, gives you the training metrics. So This one actually is a multi-classification problem, so I can see that the overall misclassification rate on the training set was about 14%. Because it's multinomial, you get the top 7 hit ratios, or the top hit ratio. So it says, I predicted the first one right, 85% of the time, which matches up with 14 on training. If you pick the top 2 in terms of class membership, it's right 97% of the time. So you can use this if you want to present multiple options, or for instance, if you're doing ad tech and you're trying to bid, this could give you the top ad places, and people are using it in ad tech for those types of cases. You can also see that the model scored about the same on the validation metrics in terms of misclassification, so it did okay, and you get kind of the same validation data. A couple other things that are available when you use it through R or Python or Scala. So you can pull out those metrics. I can pull out that validation metric, that confusion matrix, to my local machine and have it available. I can pull, in this case, what I want to do is pull a very specific metric out of it and store it. So I did that. There are ways to do, so this is feature engineering. So I'm going to create a new feature that's the tangent. There's a feature in this data set that's the slope. So it's the slope of a hill. It's actually the tangent of the slope. So feature engineering like this is available. There's all kinds of other slicing and feature engineering you can do. On the real stuff, you can do interactions. This I'm not going to run because it really doesn't help any, but you can create interactions between your factors. Those are available. There's also group buys. So if you're doing group buys and summary statistics, lots of those methods are available in the interface. And again, probably the other, I'm going to run through this real quick, but you can then go do model comparison. So I've created a couple new features. Does it actually help in this? And the answer is, in summary, no, that the data with the new features was not actually an improvement over the existing data, at least in terms of this hyperparameter set. This is available in the bleeding edge, which is a grid search. So you've got hyperparameters you need to look through. So for instance, with random forest, 2 parameters that are typical to tune are the number of trees and the depth of the trees. So we can set those with a list object. And then there's an H2O method that's called a grid search. So this does a full grid search. So this will actually build 9 different models using random forest on the training and validation, and return that whole grid of objects back to the client. So we'll run that, and so that will take a few minutes to run on my local laptop. But all of those models are then available. All 9 of those models are then available for doing model selection on, so you get a grid of those models out, and you can pull them out. In the interest of kind of staying on time, what I'll do is I'll kind of step through a couple places of where to go get H2O. So the downloads are a great place. The documentation, the latest documentation is always linked off of the download sites. So those overall H2O documentation is here. There's specific links to the R, Python documentation. If you're interested in the Java APIs, I'm going to go back. If you're interested in the Java APIs, those are all linked down here. If you're interested in the scoring, actually the scoring stuff is all up in Bleeding Edge. That is the scoring stuff is here. We have a set of booklets that are available for linear models, deep learning, GBM. These are all kind of in beta. If you're interested in running it in Spark, what we've done with Spark is we've taken H2O as a library and we've embedded in Spark, so we've made it easy to get data in and out of an H2O frame and RDDs. We'll be releasing Spark 1.5 support soon and data frame support soon. So that's what happens inside of Spark. And in terms of running on Spark, what we do inside of Spark is we sit there right along MLlib and Spark SQL. And like I said, we make it easy to get data in and out of RDDs to H2O frames. And basically what happens is H2O starts up in a special client mode on the Spark driver, but H2O clusters are start in each Spark executor. And this is showing Spark on Yarn, which is a common deployment. And so those run in the exact same JVM that Spark is running in. So it's all in process data movement that happens between the two, except when it gets sprayed across the H2O node so that it's set up to do machine learning. And people that have tried both tell us that Spark has some good MLlib stuff, especially their text classification, and H2O's kind of core algorithms tend to scale to larger data sets and run really fast because they have, like I mentioned before, a whole completely different criteria. The H2O really just wants to run, it's designed to run super fast to the point that if anything goes really wrong with your H2O cluster, it'll just shut down instead of having the overhead of high availability in it, designed for speed. Like I said, the GitHub is available. It's a great place to come to. And then on H2O AI, linked off of the main page, is both the open source support group, so Google group. If you're more into the development side, we have a Getter channel that's available that you can check out too. So I think with that, I'll stop because I've covered a lot, and I'm going to try to keep things on time. Thank you. If there's a question I can't quite hear. I can see you, but I can't hear you. Hi, Alex. Yeah. Oh, I don't. Audio's not working. Oh, that's a little better. Yes.
And right now?
Yes, that's better. Yes, good.
Okay, excellent. So hopefully right now you'll know that unfortunately we had some temporal problems with connection. Okay, but hopefully we can right now ask you a couple of questions if you mind. Well,
yeah.
Sorry, unfortunately we're still trying to figure out how to make our connection better. So okay, the questions. Okay, you told us about deep learning, and are you using GPUs in deep learning on H2O, in particular Tesla?
No, so we're currently H2O's works on CPUs only. And it has a little bit to do with kind of the target use cases. And a little bit to do with just the desire to keep it simple and run in pure Java. But currently it's CPU support only, but GPU support is on the product roadmap.
Mm-hmm. Okay, and are there any plans for GPU?
Yeah. I mean, it's on the product roadmap. We're trying. The common data that runs through H2O is not image data or time series data. Sensor data or speech data. It's usually people with business data, and the challenge with that is that business data, image data benefits a lot from GPUs because you can take it can take an image, or some matrix representation of an image. You can transfer it across the CPU, run lots of matrix operations on it, and then return the results. Whereas typically with the data that is used in H2O, you're only doing a few matrix operations on it today. But there is a desire to support images, and so that will force kind of the roadmap into GPU support. It's CPUs right now, though.
Okay, cool. And maybe you could share some insights on where then deep learning is applied in business applications.
Oh,
like Cirrus or.
So there's So I'll tell you, in terms of working with the paying customers, most of them are using generalized linear models, random forest, and GBM. The ones that are using deep learning are using it, for all the same sorts of problems. With like one of the primary use cases that we get for deep learning is people looking for fraud or intrusion detection, and so they're using. They're particularly interested in the autoencoders for looking for anomalies, and they put it in their like fraud or intrusion detection pipeline. And that's a common use case for H2O deep learning. We actually have a video that's probably linked off of our website that's PayPal using it for fraud detection.
Okay, thanks. Any more questions? People are again asking whether the service is open source and free.
Yes, so everything that I've shown you is open source, Apache version 2 license, even the Pojo. All of the algorithms you saw, the flow user interface, the R API, the sparkling water, everything is Apache v2. The company makes money by selling enterprise support for the software. But the software is all completely open source and a nice license. It's designed for adoption and quick adoption.
Cool. Any more questions? Okay, then if there are no more questions, then I would ask you to thank Hank again for him to tell us this presentation.
Have a good day, and Alex, I put my email in the chat, and you can share with everybody if there's any questions afterwards. I'm happy to take those.
Okay, thank you once again. Well, actually, this Hangout was live, and hopefully it will turn out somewhere on YouTube sometime soon. So I will share you a link too, and of course I will share a link with everyone who attended. And hopefully it will be interesting for other user groups and data scientists.
Excellent. Thank you for doing that. That'll be perfect.
Thank you once again for joining us, and have a good day.
You too. Bye-bye.
Bye.